Okay, recall that last time I told you this was the first slide that you actually need to know. Um, Although the rest of the stuff is really interesting, I know you were riveted while you were watching it, and it's going to be really useful for you when you take chemistry again, um, and you really get into molecular orbital theory. So, what else do we need to be able to do with hybridization? Um, First of all, we need to be able to assign it. All right, that's just a mechanical thing. If you can find electron pair geometry, you just associate it with a hybridization. Okay, and we have those three hybridizations we need to know. That's it. Now, what do we do with it? Well, we want to use these hybrid orbitals to make bonds between atoms. Okay, and it turns out there are going to be two kinds of bonds that we can make based on two different ways that orbitals can overlap with each other. So bonds essentially require orbitals to overlap with each other. Orbitals on two different atoms to overlap with each other. And essentially they then kind of recombine and become new orbitals. So that's the first thing to remember, is that bonding really requires orbitals on neighboring atoms to overlap. And they can overlap in two different ways. All right, the first kind of bond that they can make is called a sigma bond. And anytime you have a bond between two atoms, the first bond is a sigma bond. So any single bond is just a sigma bond. A double bond would be a sigma bond plus another kind, which is mentioned below, which is a pi bond. So in a sigma bond here, the orbitals on neighboring atoms essentially point directly at each other. And overlap right in between the two atoms. Whereas in the second scenario, there's going to be a different way that they overlap. So for example, if I have two hybrid orbitals, they could point directly at each other. So hybrid orbitals, remember, have a shape kind of like this, where there's one big lobe and then a tiny little lobe. So they really point in one direction. So a sigma bond would be made between one orbital, I'll draw in black, and one orbital I'll draw in red, on two neighboring atoms, and they'd point at each other, and then they overlap. And sigma bonds are made by hybrid orbitals and or just s orbitals if you're talking about hydrogen. Hydrogen never has hybrid orbitals because hydrogen's just working with energy level 1. But sigma bonds are generally made by hybrid orbitals. Now, if you have a double or a triple bond, you can make what are called pi bonds. So pi bonds are made by overlapping p orbitals. They're parallel to each other. All right. So I could have a p orbital on one atom like this. And then on a neighboring atom, I could have a p orbital that overlaps with it, sideways like that. So here, the two orbitals are overlapping in two different regions, but notice they don't overlap directly in between the two atoms. They don't overlap directly in between the two nuclei. So a pi bond kind of sits above and below the two nuclei, but still sort of between them. So that's how we make bonds using the orbitals in a hybridized atom. We can make sigma bonds and pi bonds, and then we need an orbital for lone pairs to live in. And so lone pairs generally live in hybrid orbitals that don't overlap with anything. So if you have a hybrid orbital that's overlapping with something, it's going to make a sigma bond. If you have leftover p orbitals that are overlapping with other leftover p orbitals, that's going to make a pi bond. And if you have a hybrid orbital that overlaps with nothing, then lone pairs will occupy those. If an orbital doesn't overlap with any other orbitals, it's essentially non-bonding, which is what we call those electrons that are lone pairs, non-bonding pairs. Okay, so let's apply that description. If we want to apply it pretty simply, we're always going to start with the Lewis structure. So this is why we practice Lewis structures a bunch. So you start by drawing a Lewis structure, you figure out the geometry. Once you know the geometry, you can determine the hybridization. Once you know the hybridization, you can figure out where, well, you can, from the Lewis structure, just figure out where the sigma and pi bonds are. But then using the hybridization, you can describe what two orbitals are actually creating each bond. So what two orbitals are overlapping to make a bond. So let's start with a simple molecule like C2H6. Take a moment, draw yourself a Lewis structure. I'll draw one up here while you do it. Okay, hopefully you drew something like this. Now I'm going to determine the geometry. What's the geometry of each of those carbon atoms? Not pyramidal. It's tetrahedral, yeah. These are both going to be tetrahedral. Pyramidal would be if they were bonded to 3 atoms and had a lone pair. These are bonded to 4 atoms. Either way, the electron pair geometry would be tetrahedral. Okay, so I have tetrahedral atoms. I look back very quickly. Oh, that's going to correspond to sp3 hybridization. Okay, so each one is sp3 hybridized. What kinds of bonds are shown up there? All sigma bonds. There are no pi bonds here. I know there are no pi bonds because I don't see any double or triple bonds. Also, I determined the hybridization was sp3, and when there's sp3 hybridization, how many p orbitals are left over to make pi bonds? 0. So when something's sp3 hybridized, it's not making pi bonds. So these are going to be all sigma bonds. So I'm going to do my best to just draw it. I have carbon atom here and a carbon atom here. And each one is sp3 hybridized. I'm not going to do the 3D structure very well. But they're each going to have an orbital pointed towards each other in the middle. Um, and for simplicity's sake, I'm not going to draw the little parts of the hybrid orbitals. So they have the big lobe and then that little tiny part. I'm not going to draw the little tiny parts because they're not going to be important to the bonding. So here I have in between the two atoms a sigma bond from a carbon sp3 plus another carbon sp3. And then each one is going to have 3 more sp3 orbitals pointed like a tetrahedron, which of course I can't draw very well because it's 3 dimensions and I'm trying to draw these orbital things. But I'll just draw them kind of like that. And then I have the hydrogens. What orbital would hydrogen be using to make bonds? What's the only orbital available to a hydrogen atom? The 1s orbital. So I'd have my hydrogen atoms, and they're going to have 1s orbitals overlapping with these hybrid orbitals. So now each of those is a sigma bond from a carbon sp3 orbital plus a hydrogen s orbital. Now, at this point in your chemistry career, I don't want you worrying about having to reproduce these drawings so much. But I would like you to start picturing this in your head a little bit, where you can imagine the hybrid orbitals, imagine them overlapping to make bonds. All right. What if I change, instead of C2H6, I make it C2H4? Take a moment, draw yourself a Lewis structure for C2H4. Okay, how does C2H4 differ from C2H6? Now it's got a double bond. All right. C2H4 has got a double bond. My hybridization of each carbon atom, or sorry, my geometry first, geometry of each carbon atom is going to be what? Not pyramidal. Pyramidal would be if there were 4 electron domains. If I look at one of these carbon atoms, how many electron domains does it have? Only 3 domains. So 3 domains, which means geometry of trigonal planar or flat triangle, if you're not trying to impress anyone. So trigonal planar, which means I look back, oh, that's going to correspond to sp2. So they're sp2 hybridized, and they have 1 leftover p orbital. Now, why is it important that they have 1 leftover p orbital? Well, in a double bond, I should have 2 different kinds of bonds. The double bond is going to consist of 1 sigma bond and 1 pi bond. So I'm going to actually make 2 drawings for this molecule. I'm going to make one drawing of the sigma bonds, and then I'm going to make a separate drawing for the pi bond, because it's hard to draw them both on the same picture. And then I'm going to show a model of what this molecule looks like. All right, so first, my drawing of the sigma bonds. I have my 2 carbons, and I have my 4 hydrogens, and they're all in the same plane. I'll stick with green for my carbon hybrid orbitals. So just like before, the 2 carbon atoms make a sigma bond using their hybrid orbitals. And then they're going to make sigma bonds with the hydrogens using those hybrid orbitals. And every time I say hybrid orbital, I feel like it reminds me of the rural juror, if you're a 30 Rock fan. Because I feel like my mouth is full of marbles. All right, so same situation. Now I have sigma bond from a carbon sp2 and a hydrogen s orbital. I have 4 of those, and then in the middle I have my sigma bond from carbon sp2 plus carbon sp2. So every bond in the molecule we can imagine being made from 2 atomic orbitals. All right. So now, if I want to draw the pi bonds, there's a reason I'm going to use a different drawing to represent the pi bonds, and that's that the pi bonds are going to be perpendicular to the plane of the molecule. So all these sigma bonds are in one plane. And you may remember from last time I showed a model of an sp2 hybridized atom. Here it is again. The p orbital, which is in green here, is perpendicular to the 3 sp2 orbitals, which are around the middle. All right. So there's my model again. The p orbital is perpendicular to the sp2 orbitals. So when I want to represent the pi bond, that's going to be perpendicular to all those sigma bonds. So far I've been representing this with my sp2 orbitals in the plane of the page, and the p orbital is coming directly at you. So here's the model in that orientation, and you can't see the p orbital very well because it's coming directly at you and going away from you. So again, the orientation that's shown on the screen is like this, with the p orbital directly toward you and away from you. Now if I want to show the pi bonding, I'm going to rotate my view. So instead of looking at the molecule like this, I'm going to flip the molecule up like that so the p orbital becomes more obvious. So go from this orientation to that orientation. So in that orientation, what I'm going to do is just draw a line to represent the sigma bonds. And now my hydrogens are going to go into the page and out of the page. And I'll be left with my 2 p orbitals. And p orbitals, a lot of times we draw p orbitals as a skinny little peanut like this. It's actually not a great representation. We do that for convenience, but they're actually a lot fatter than we give them credit for. So really a p orbital should be more like this. So that when I have 2 of them next to each other, and I'm kind of not pleased with that drawing, because they should be symmetrical. But when I have 2 p orbitals next to each other, they find a little bit of space to overlap, and that's what creates the pi bond. So I built a few models of C2H4 that I'll pass around. So here's one. We've got, you can see the sigma bonds are just the little gray bonds. And then the pi bond would be the overlap of these two p orbitals that are in pink. So there's one model you can check out when you come to the classroom. You see the pi bond perpendicular to the plane of the molecule. Here's a second one. Same idea. And then this one, which I think is really cool because it's nice and sturdy. Here you can actually see the sigma bonds represented by these kind of gray bulging orbital things. So the sigma bonds are represented there, and then the pi bond is this purple and pink thing. So here you can see I've got my molecule with the sigma bonds, and now the pi bonds in pink and purple. So let's pass those around. Question? Ah, outstanding question. So the question is, the way I drew it, it looks like the sigma bond has more overlap between the two orbitals than the pi bond does. And does that mean it's stronger? And the answer is definitively yes. So sigma bonds, because there is better overlap between the orbitals, and because the two electrons reside directly in between the two nuclei, or at least there's increased electron density directly between the two nuclei in the bond, that's going to be lower potential energy than when you have increased electron density up above the plane of the two atoms and below the plane of the two atoms. So sigma bonds in general are stronger than pi bonds. Absolutely. So the question is, here I wrote the pi bond comes from carbon p plus carbon p. For a pi bond, will it always be some element p? If it's a different element than carbon, will it always be something p plus something else p? And the answer is yes. Pi bonds come from overlapping parallel p orbitals. So no matter what the atoms are involved, you always know how a pi bond is made. So the question is, would it be p2? Well, there's no such thing as a p2 orbital. Sometimes when we're giving electron configuration, we'll say, 2p2 to say that there are two electrons in there. But when we're talking about making the bonds, we're ignoring the number of electrons for the time being and just looking at the overlap of the orbitals themselves. All right, other questions about pi bonding? So I said you don't need to be able to draw these necessarily. I do ask you to do a little bit of drawing on the problem set, but the skill that you do need to have is to be able to look at a molecule and identify where there are sigma and pi bonds. So really, you need to know how to assign hybridization, and then you need to be able to count sigma and pi bonds in a molecule. All right, so C2H2, if I take away two more hydrogens, quickly draw yourself a Lewis structure. So the question is, how do I know when to bend the ends of the structure? I'm not sure what you mean. Oh, the question is, should C2H2 be bent? So let's draw the Lewis structure. And then let's identify the geometry for each of these carbons. So how many domains on each carbon? 2 domains. So what's their geometry? Linear. So they shouldn't be bent. It should be all in a straight line. Linear geometry is going to correspond to SP hybridization. And when I have SP hybridization, we said that's going to leave 2 leftover p orbitals. Why is it important that I have 2 leftover p orbitals in C2H2? Because I've got to make 2 pi bonds. I have a triple bond. A triple bond is going to consist of a sigma bond plus 2 pi bonds. So again, I can draw my sigma bonding, and I'd have a sigma bond between the 2 carbons. Each carbon is going to make a sigma bond to a hydrogen. And then I can make a drawing of my pi bonds. Now my pi bonds are going to be a little more challenging in this case because my 2 pi bonds have to be perpendicular to each other. If I go back to my model of an sp hybridized atom, in an sp hybridized atom, I've got my sp orbitals that are across from each other. In this model, they're pink. And then I've got my 2 p orbitals, 1 and 2, and those are perpendicular to each other. So I've got the line of the molecule, and then I've got 2 p orbitals that are perpendicular to those. So here, sp going left and right, and then I've got 1 p orbital going up and down there, and 1 p orbital coming towards you and going away from you there. It's going to be really hard to draw. I've built some models, again, that you should check out when you come to the room. So here, I've made one of my pi bonds blue, and that's going up and down. And then one that's green is coming towards you and away from you. And if I rotate the molecule, you can see the green one and not the blue one. So 2 pi bonds perpendicular to each other. Same thing here. I made a purple pi bond and a pink pi bond. And they're perpendicular to each other. All right, so I've drawn the sigma bonds. Now I'm going to try and draw I'm going to pass around the models while I attempt to draw the pi bonds a little bit. So I'm drawing one pi bond in purple, and I'll draw the other pi bond in red, but here my 2 orbitals are going into and out of the page, and it's hard to draw them. So I'll say there's my red pi bond that goes into and out of the page. And my purple pi bond that's going up and down. The question is, do they bond over each other? Not really. If you look at the model, you'll see they're perpendicular. It's just I don't have a good way to draw that. The 2 pi bonds are not overlapping with each other. That's right. They're 2 separate bonds in separate space. Now notice, we can't have any more left parallel p orbitals, so 2 pi bonds is the maximum we can make. So this is why we can make triple bonds, because we can have a sigma and 2 pi's, but we'll never have a quadruple bond because we can't make a third pi bond, and we can't make a second sigma bond. In some rare cases, you can make transition metal atoms, use their d orbitals to make what's called a delta bond, and so you can make a quadruple bond, but it's not something that you're likely to run into anytime soon. All right, so we have sigma bonds, we have pi bonds. What if I make HCN instead of C2H2? So the Lewis structure for HCN is going to have a triple bond between carbon and nitrogen, just like C2H2 did between carbon and carbon. The difference is now nitrogen has a lone pair. So it turns out I have pretty much the same bonding picture as I did before. I've got a pi bond, I've got a triple bond, which is going to be a sigma bond plus 2 pi bonds. My sigma bonding will look just like it did in C2H2. I'll use a different color for nitrogen's orbitals. Purple for hydrogen. We'll make nitrogen red. So notice both of these are sp hybridized. I didn't go through all the steps of determining hybridization there, but you should get to the point where you start to determine the hybridization quickly. So just like in C2H2, I have sigma bonds. I have a sigma bond between the carbon sp orbital plus the nitrogen sp orbital. I have a sigma bond between carbon and hydrogen. But now nitrogen has a leftover sp orbital that's not overlapping with anything. So what goes there? That's where the lone pair lives. So the lone pair lives in that sp orbital. So the question is, isn't that side of nitrogen where the stumpy part of the sp hybrid orbital would be? Well, so remember, nitrogen's got 2 hybrid orbitals. One pointed to the left, and it's got a stumpy part that goes to the one pointed to the right, it's got a stumpy part going to the left, and then another one pointed to the left with a stumpy part that goes to the right. I chose not to draw the stumpy parts on either one because they just get in the way of the picture. But yeah, there is a stumpy part on each side, but there's also a big lobe on each side. So the question is there a difference between bonding an s orbital and a hybrid orbital compared to bonding 2 hybrid orbitals to each other? I mean, there are mathematical differences, but the result is a sigma bond. Sigma bonds mean there's overlap directly on what we call the internuclear axis, the line between the 2 nuclei. That's essentially what a sigma bond is. And so either way, it's a sigma bond. So we can treat them as the same. I mean, of course, hydrogen's orbital energy is different. Its orbital size is different. That does affect the bonding to hydrogen. But at this level, we'll just describe them as being equivalent. They're sigma bonds. So the question is, in the sp orbital where I have like the big part and then I have the little stumpy part, where does the nucleus lie? You can think of the nucleus as being right in the middle where the node is. It might be slightly shifted, but that's of no consequence to us. I think the node actually is in the middle, but so then the pi bonding for HCN would look exactly the same as the pi bonding for C2H2. We would just get one of the hydrogens off of our picture. So the pi bonding picture would just be exactly the same as C2H2. Now again, I don't want you worrying about drawing these things. I'm drawing them so that you have something of an idea in your head and giving you the model so you have something of an idea in your head. But as far as what you need to be able to do, just identify sigma and pi bonds from a Lewis structure. Now, this separation between sigma and pi bonding is going to allow us to give a more complete description or a better description of what resonance really is. So we've drawn resonance structures before, and we said it seems like there's a double bond that's moving between two places. Where resonance really is the fact that sometimes we have pi bonds that are spread over more than two atoms. So we think of covalent bonding in our simplest idea. When we introduce the idea of covalent bonding, we say it's between two atoms. A covalent bond is always between two atoms. But like everything else in nature, like our oversimplification works for a while, and then we want to describe certain situations, it breaks down. So we need to come up with a more complicated description. And so when we have resonance structures, what that really means is we have pi bonds that are spread over not just two atoms, but 3 atoms, or 4 atoms, or 5 atoms, or 6 atoms, or sometimes 1,000 atoms. And we call that delocalized pi bonding. So whenever you have 3 atoms near each other that all have parallel p orbitals, or 4 atoms that all have parallel p orbitals, you'll see this phenomenon where you have delocalized pi bonding. So we'll go back to O3 for practice. Try and draw the Lewis structure for O3, including resonance. Okay, hopefully you drew something like this. You could always refer back in your notes. But my Lewis structure for O3 would look like this, and I have an alternate resonance structure where it appears that this lone pair became a pi bond and this pi bond became a lone pair. I'm drawing those red arrows. That's a formalism that we use in organic chemistry to show the movement of electrons. And when you have 2 resonance structures, you can always imagine drawing those. You don't need to worry about how to use those. But I put them in there so you can kind of visualize the relationship between these 2 structures. If you imagine this lone pair on the right-hand oxygen becoming a pi bond, and then the pi bond becoming a lone pair. What that shows me is I have a pi bond that's kind of present in both places. So in the actual structure, there's a pi bond that's present in both places. And there's actually a lone pair that appears to be present on both of the outer oxygens. So how can we describe that? Well, what we would say is, if I draw my 3 carbon atoms, we'd say that they're on my carbon atoms, 3 oxygen atoms. Luckily, that's an easy fix. On each one, there's going to be a p orbital that's parallel to the other 2. So I'm going to have a p orbital on the center one, p orbital out here, and a p orbital out here. All 3 of those p orbitals are going to be aligned so that I have pi bonding down here and pi bonding up here. It's 1 pi bond spread over all 3 atoms. And I did a quick little conversion of my C2H4 model. So now I have my 3 oxygen atoms, gray sigma bonds, and then these other gray things with no atom at the end would represent the lone pairs. So my molecule is really in a plane. And then I have this pi system spread over all 3 atoms. And that pi system includes this pi bond that's spread over all 3 and the lone pair that's actually shared between the outer 2. So I'll pass this model around. So my purple and pink there represents that single pi bond spread over all 3 atoms. And then the gray represent the sigma bonds and the lone pairs. See, the central oxygen has 1 lone pair. It's in my hand now. The outer 2 oxygens have 2 lone pairs each. And then this pi system would include the pi bond and that 3rd lone pair that seems to be floating between the 2 outer atoms. Question? So the question is, does that mean the orbitals are so big that the outer 2 oxygen p orbitals actually overlap with each other? And the answer is no, they don't necessarily need to overlap with each other. As long as there's kind of an unbroken chain of these parallel p orbitals, the relationships between the neighboring atoms can end up spreading out over more. They both just have to touch the one in the middle. Both of the outer p orbitals just have to overlap with the one on the middle oxygen. Other questions? So the question was actually leading to the next slide, which is dealing with benzene. So this delocalized pi bonding doesn't have to just be between 2 atoms at a time, or 3 atoms at a time. It can be 4 atoms, 5 atoms, 6 atoms. So in a molecule like benzene, benzene can be described by 2 resonance structures. And I'm just going to draw the skeletal structures right now for the sake of time and space. But benzene can be described by those 2 resonance structures, and I apologize for that horrible hexagon on the right, which shows that there's delocalized pi bonding in the ring, and it turns out all 6 carbon atoms share those 3 pi bonds. So there's 3 pi bonds that are shared by this ring, and so benzene ends up having like a donut of electron density on top, and then a second donut of electron density on the bottom, which is really hard to draw. After everyone's had a chance to see the simple models, I can actually build a model of the delocalized pi bonding in benzene from the models that we have here. This can be extended even more. We've talked about graphite a little bit. Graphite is essentially like a whole bunch of benzene rings just arranged into a long sheet. So graphite has delocalized pi bonding along the entire sheet. which is why graphite conducts electricity, even though we don't expect that from a network solid. It's because it has this delocalized pi bonding spread over the entire sheet, which just looks like a whole bunch of these rings stuck together. All right. I think that's enough mind-blowingness for one day. We'll finish this up tomorrow.